In this slide, we are going to talk about some problems which related to process synchronization. One problem is called deadlock. So when programmer use a process synchronization mechanism carelessly, so it can cause several processes it just stuck there, and no one can make any progress. So here shows us an example, and there are two semaphores S and Q, and both of them are initialized to 1. For process P0, it calls the synchronization operation like this order. So wait S operation, wait Q operation, and then get into critical section, and then signal S operation and signal Q operation. On the other hand, process P1 calls the synchronization operations in reverse order like that. It will do wait Q operation first, and then wait S operation, get into critical section, and then signal Q operation and the signal S operation. So assuming P0 has been put onto the CPU first, then P0 calls wait S operation, and semaphore S will be decreased to 0 and out of the wait S operation. Then P0 is interrupted by P1, so P1 calls wait Q operation. Then semaphore Q is decreased to 0. Then P1 calls wait S operation. So since S is 0, so P1 will be blocked until P0 calls signal S to release the value of S to 1. Then P1 is interrupted by P0. So P0 waits called the wait Q operation. However, P0 will be blocked as well because Q is also 0 now. So P0 is waiting to be released until P1 calls signal Q operation. So from this point, you may already know the problem. So P0 is waiting for P1 to call signal Q. P1 is waiting for P0 to call signal S. So both of them are waiting for each other to release the semaphores. So for this problem, we call it a deadlock because no one can make any further progress. So in order to avoid this problem happening, so we try to operate these semaphores in same order. Otherwise, the deadlock problem will be happen with a very high probability. Another problem which related to deadlock is called starvation. So sometimes we also call it indefinite blocking. The formal definition of starvation is that the processes are suspended in some queue forever and never get a chance to be executed on the CPU. So normally, when the deadlock happened, it can cause the starvation problem. So let's look back to the previous example. For both P0 and P1 are waiting inside the waiting queue corresponding to semaphore S and Q respectively, right? So both of them will be stuck at the waiting queue forever and never get a chance to be executed on the CPU. So which is a really good example of starvation. However, on the reverse side, it doesn't mean all the starvation problems they are caused by deadlock. So the following situation give us an example, which is called priority inversion. So in this case, we do not have a deadlock, but the starvation problem still happened. So actually, this is a scheduler problem, which means the process with a lower priority holds the resources or the lock, which is needed by the process with a higher priority. So let's look at an example. Suppose we have 3 processes, L, M, and H, just like I draw at the bottom of this slide. And their priorities are just like their names, which are lower, middle, and highest. So L holds the lock that either is a spin lock or mutex lock, so which is needed by H. Since H is blocked by the lock, so therefore the scheduler will choose M and put M on the CPU to be executed. So due to the priority of M is higher than L, so L cannot get a chance to be executed on the CPU. Therefore, L cannot release the lock needed by H, so which causes H suspended in the waiting queue for a very long time. If the processes with middle priority continually join in the system, so H can be blocked in the waiting queue for an infinite time. However, for this priority inversion problem, L and H eventually can be executed on the CPU. So that is the difference between the deadlock and the priority inversion. But how to solve the priority inversion problem? So we can solve it through priority inheritance protocol. So we still use the same example. Since the system noticed that the lock needed by H is held by L, so instead of fixing the priority of each process, so system will temporarily increase the priority of L to be the same as H. So after H gets the lock, then change the priority of L back to default right after that. So through this way, it can solve the priority inversion problem and also to protect the original priority of each process. So now you may understand why we call it a priority inheritance protocol, because we let the lower priority process who hold the lock temporarily inherit the priority of a higher priority process, so who need the lock. After releasing the lock, change the priority back to the original one.